Hello. Today we are going to finish section 11.5. Section 11.5 is application analysis of algorithm efficiency 2. This is part 3. This is part 3 of the section. Um, this is chapter 11, analysis of algorithm efficiency. In the last class we discussed binary search algorithm. In this class, we are focusing on merge sort. This is the second sorting method that we learn in this chapter. All right, just go forward. Note that it is much easier to write a detailed algorithm for a sequential search than for binary search. So you know these search. We have already learned this sequential search we already learned, and the binary search we learned these two. You know, writing algorithm for the sequential search is easier than writing algorithm for the binary search. You have seen that. Yet binary search algorithm is much more efficient than sequential search. All right. Such trade-offs often occur in computer science. That means there are two algorithms. One is easier to write, but at the same time it is less efficient. There's another algorithm which is hard to write, but it is efficient. All right. So such trade-offs are always in computer science, as you know. Frequently, the straightforward solution to a problem is less efficient than a clever solution that is more complicated to describe. That's true, right? You know this. Straightforward solutions are less efficient. At the same time, the clever solutions are more complicated to describe. This is common sense. We know that. All right. We know one method for sorting, which is insertion sort. You all know about insertion sort that we learned in section 11.3. We learned insertion sort in 11.3, which is a sequential method. This sort is used for ordinary situations. Okay, this sort is used for ordinary situations. This insertion sort is easy. An easy sorting method. Since it is easy, it is less efficient. Okay, it's an easy sorting method, but it is less efficient. All right, now let's go to the next sorting method that we're going to learn in this class, which is merge sort. Can a divide and conquer approach, so this approach in the merge sort is called the divide and conquer. Can a divide and conquer approach be used to find a sorting method more efficient than this? All right, the answer is yes. So we are going to find a divide and conquer method for sorting. All right, so that is the merge sort that we're going to learn here. In fact, over the past few decades, computer scientists have developed several divide and conquer sorting methods, all of which are somewhat more complex to describe but are significantly more efficient than insertion sort. Okay, more efficient, more complex to describe. All right, you know that if it is more complex, it is more efficient, of course. All right, it is not like the insertion sort. The opposite is the insertion sort, less complex, less efficient. One of these methods is called the merge sort. All right, so this sort is a recursive sorting method. Imagine that an efficient way for sorting array of length less than k already known. How can such knowledge be used to sort an array of length k? All right, let me read it again. Imagine that an efficient way of sorting an array of length less than k already known. So let's say you have an array of k elements. Let's say you have an array of k elements. Okay, let's say there are k elements. Okay, so you have to sort this. The sorting of that one is not known, but the good thing is you know how to sort these sub arrays. Okay, this is less than k, sorting, this is sorted, this is sorted. All right, so you have to sort this then. Okay, let me write like sorting of k elements. Okay, which is unknown. Okay, here, how can such knowledge be used to sort an array of length k? All right, which I have already explained. Okay, so this is the merge sort. One way is to suppose the array of length k is split into two roughly equal parts and each part is sorted using known method. Is there an efficient way to combine the parts into a sorted array? All right, that means just consider this is a subsequent step. This is a subsequent step. So you are given this sub array which is already sorted, and you are given that sub array which is already sorted. Now you have to merge them such that this array is sorted. You have to merge them such that this is sorted to be sorted. Right? You have to sort the resulting array. So this is a subsequent step. In the previous step, you have to sort this one and you have to sort that one. Even in the very first steps, you have to sort subsequent sub arrays. Let's say you are given this sub array which is already sorted, and you are given that sub array which is already sorted. All right. Now you have to merge them such that the merge array is already sorted. This is very easy. The sorting part is very easy. That I'm going to explain in the next few slides. Okay. Before going to next few slides, let me explain it roughly here, roughly in this slide, and then I will explain it with details in each of the following slides. This is what we do. So we have this array sorted and that array sorted. Then what we do, we just take the bottom element here and bottom element there. So we compare them. Okay, so we compare 2 with 3 and then find the least. The least is 2, so you just bring 2 here. All right, and then you compare the bottom array of these with the bottom array there, that is that. So then compare what is the minimum. So 3 is minimum, so you bring 3 here. All right, so you bring 3 here. All right, then go to the next least element. Let me use a different color. You could see this is the least element in the bottom element in that array. This is the bottom element in that array. Least of that one is 5. You bring 5 here, and then next go to this element in that array and this element of that array. The both are 6. It's a tie. You can choose any one you want. Okay, and then just go to the least the bottom array of that the bottom element of that array and the bottom element of this array. Choose the least among them into this location. So you keep on doing that until you fill the entire array. Okay, until you fill this entire array. So this is the procedure. Merging is very easy. That I explain in the next few slides. All right, let me read one by one. Imagine that the elements of two ordered subarrays. So these are the two ordered subarrays. The subarray which was right here, and this is the subarray which was right there. Okay, so you had two subarrays are written on slip of paper. So just assume that you are just practicing this way. You are just following this way. You just write them on slips of papers. Why we write them? To make them easy to move around. Place the slips for each subarray in two columns on a tabletop, one at the left and one at the right. Okay, so one at the left, one at the right. Right. Along the bottom of the tabletop, set up 8 positions into which the slips will be moved. Then one by one bring down the slips from the bottom of the column. Okay, so this is these are the locations that we are going to fill. All right. At each stage, compare the number on the slips currently at the column's bottom and move the slip containing the smaller number down into the next position in the array. If at any stage the two numbers are equal, the slip on the left to move into the next position. All right, so we had that situation. We had two equal. In our case, 6 was equal to that 6. This 6 was equal to that 6. Then we just follow the procedure explained. Give me a second. Explained right here. All right, so let's move to the next slide. And if one of the column is empty at any stage, just move all the slips from the other column into the corresponding position one by one in order. Okay, that's what we did. Okay. The process of merging is efficient because the total number of comparisons needed to merge two subarrays into an array of length k is just k minus 1. So you need only k minus 1 comparisons. All right, so let's count those k minus 1 comparisons. You compare, you compared this with that. Okay, so then you took this, you took 2 then, and then you compared 5 with 3. Okay, so that's the next comparison. You took 3, and then you compared 5 with 6. Then you got 5, and then you compared this 6 with that 6. You got 6, and then you compared that 6 with that 8, and then you got 6, and then you compared 8 with 7. You got 7, and then you compared 8 with 9. You got 8, and then remaining one was 9. So how many comparisons are there? 1, 2, 3, 4. Let me write them above. How many comparisons? Number of comparisons equal number of arrows. 1, 2, 3, 4, 5, 6. 7. There were 7 comparisons. All right. There are 8 elements but 7 comparisons. Okay, that means number of comparisons equals k minus 1. Okay, number of comparisons equals k minus 1. All right. Observe that at each stage, the decision about which slip is moved is made by comparing the number on the slips currently at the bottoms of the 2 columns, except when one of the column is empty, in which case no comparisons are made at all right? So that's why we have k minus 1 comparisons. Thus, the worst case, there will be one comparison for each of the k positions in the final array except the very last one, or a total k minus 1 comparisons in all. Okay, so I explained that there should be k, in the worst case there should be k minus 1 comparisons. So keep in mind, this is the worst case. In the worst case there are k minus 1 comparisons. All right. Now we are going to learn about the algorithm. The merge sort algorithm is recursive. That means you can see that this is an intermediate step. In this intermediate step, these arrays are already sorted. But in the previous step, you have to merge. You have to sort these arrays. All right. So you have to sort these arrays in the previous step. But in the current step, you can assume they are sorted, but you have to sort only this. That's why it is recursive. That means one step depends on the other step. All right. One step depends on the other step. At each stage, the length of the array that is input into the algorithm is shorter than the previous stage. You know that. So that ultimately the algorithm has to deal with only with arrays of length 1, which are already sorted. Especially merge sort works as follows. Okay, so this is the way the merge sort works. Given an array of elements that can be input into order, if the array consists of a single element, leave it as it is. It is already sorted. Otherwise, you have to follow these 3 steps. The first step is divide the array into 2 sub-arrays of nearly equal length as possible. Okay, so you have to divide the array into 2 sub-arrays nearly equal lengths with nearly equal length. All right, then use merge sort to sort each sub-array. You use merge sort to sort each sub-array. Then merge the 2 sub-arrays together. All right, so these are the 3 main steps in the merge sort that is explained in this flow chart. So you can understand these 3 steps very well here. So let me go to the next slide so I can explain everything again. So let us assume that this is the given array to you. So that's the given array to you. Now you have to make 2 equal size or nearly equal size sub arrays. So I could cut like that. So I take this one over here, that one over here, and again I just cut right here and take this one over there, that one over here, and cut like that. This one over here, that one over here, and then cut like that, cut like that. Okay, now I have singleton elements. I have to do this splitting until I get single elements. All right. Now I have single elements. From there, I'm starting merging such that the merge array is sorted. All right. Now I have 5 here, 2 here. So I have to bring the smallest element first. So I bring 2 here and 5 there because 2 is small. And then for the next 2 elements, it's 4 here, 6 here. So I bring 4 here and I bring 6 there. And then 1, 3, they are already sorted. So I put 1, 3. Then 2, 6 already sorted, 2, 6. Okay, so that's how I merge them in this step. So this is merge, these two are merged, these two are sorted, those two are sorted, sorted. Now I have to merge these two such that the resulted array is also sorted. Okay, for that I can use the previous merging step. I could use this merging step there. Okay, I'm using this merging step again and again. Okay, so now I'm going to merge them. I'm going to merge this with that. All right, so I compare the least element of this one with least element of that. So the least is 2, I keep 2 here. And then I compare this 4 with that 5. And then least is 4, I keep 4 here. And then I compare 4 with 6, sorry, 5 with 6. The least is 5 and then I put 6. All right, so the sorted order is 2, 4, 2, 4, 5, 6. Now come here. Now I do the same procedure. I compare this with that. 1 is small, I put 1 here. And then I compare 2 with 3. 2 is small, I keep 2 here. And then 3 with 6. 3 is 6. 3 is small, you put 3 here. And then 6. Okay, so that sub-array is also sorted. And again, I follow the same procedure to sort this, merge this and that. All right, I merge this sub-array into that sub-array and get this long sub-array. Okay, so this is the output. This is the output that is the sorted version of this. Okay, so this is the output which is the sorted version of that. Okay, now you can see merge sort is very easy to understand. Everything I explain here is given in this recursive set of equations, set of steps, recursive steps. All right. Now let's go to the next slide. As in the case of binary search algorithm, in order to formalize merge sort, we must decide at exactly what point to split each array. Given an array denoted by the first element is that, which is denoted as a of bot, and a of bot plus 1 dot 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 a top. So these are the elements. They are like maybe 3, 4, 5, 6, 1, 2, like that. So this is actually a of bottom, and this is actually a of top. Okay, so you denote the elements like that. The first element is a of bot and the last element is a of top. Then we define the mid element as top plus bottom divided by 2 and the floor function of that. Okay, so in this case the mid should be top plus bottom divided by 2 and the floor function. So actually it is 2, I'm sorry, not 2, I'm talking about the locations. The locations are, here the location is 1, 2, 3, 4, 5, 6. I use green to denote the location. Okay, so it should be 1, top should be 6 plus 1 divided by 2, and the flow function, which is 6 plus 1 is 7. 7 divided by 2 is 3.5. The flow function, which is 3. So this is the mid element. All right. So this is the A of mid. All right. Now what we do is take the left sub-array to be a bottom plus 1 dot a mid. So you take this to be the left sub-array, and that to be the right sub-array. Okay. So let me mark the left sub-array by orange, and then the right sub-array by blue. Okay, which is marked here. All right, so that is here, and then we have the merge sort. Okay, this is the algorithm, merge sort algorithm. This algorithm is same as that we have already discussed. So I'm not going to explain this algorithm because I already explained this algorithm. So if you are going to code this, so this is what you need to code. So this algorithm provides all the loops that you have to use. There's a while loop, and then you could use if loops inside. So this is the algorithm if you would interested of coding that. Otherwise, we have learned the technique so far. Okay, so by now we have clear idea how the merge sort works. So let's go to the next slide. In this slide, we are going to derive a formula for the efficiency of the merge sort. Derivation of this formula is again easy thing here. Let me read it. To derive the efficiency of merge sort, we just define mn. Mn is the maximum number of comparisons used when merge sort is applied to an array of length n. So we denote mn as that. Mn is the maximum number of comparisons used when merge sort is applied to an array of length n. So let assume that the length of the array is just 0. That means no elements in the array, because no comparisons are used when merge sort is applied to an array of length 1. M1 should be 0. Okay, so number of maximum comparisons is 0 when you have only one element in the array. And that is the initial condition. You could say that is the initial condition. Also, for any integer k greater than 1, consider an array a of bottom, comma a of bottom plus 1 dot up to a of top of length k that is split into two sub arrays. So these are the two sub arrays. This and that, where the mid should be like this. So this is the mid, like we learned early. So mid is the flow function of bottom plus top divided by 2. And then in exercise 24, you are asked to show that the right subarray has length flow function of k over 2, and the left subarray has the length of ceiling function k over 2. Let me write them, otherwise you might think they are same. So this is the flow function, flow of k over 2. This is ceiling function, ceil of k over 2. Okay, as an example, 5 plus 2 ceiling function is a ceiling function of 2.5, which is 3. Here you take the largest integer, the next largest integer from 2.5. Okay, the next largest integer from 2.5, which is 3. All right. So that is the ceiling function. This is done in exercise number 24. So because of that reason, I'm not going to show this, but I'm going to use that result here. Okay, so this is an easy exercise. It is in your textbook. By using this exercise, in this exercise, you're going to show this right sub-array has the length this, and the left sub-array has the length that. All right. From the previous discussion of the merge process, it is known that to merge two subarrays into an array of length k, at most k minus 1 comparisons are needed. So we have already learned this. Let's say you are merging an array of k elements, then at most k minus 1 comparisons are needed. All right, so you learned that. Now we are going to learn the number of comparisons. Okay, the number of comparisons when the merge sort is applied to an array of k equals, you divide that array of k into two sub-arrays. The first one is the left sub-array, that is the left sub-array. So this is the right sub-array. Okay, so you divide that into left sub-array and right sub-array. You have to compute a number of comparisons in each sub-array, in the left sub-array and right sub-array. And then you have to compute the number of comparisons to be done in order to merge these left and right sub-arrays. Okay, so the number of comparisons required to merge them. All right. We have defined that this to be mk. We have defined that. We have defined that to be mk. So this is actually from exercise. It is from previous exercise. Number of comparisons when merged sort of apply to an array of length k over 2. And then this is again the next sub-array, same amount, but it is the ceiling function. You can recognize the difference. So this is, keep your eye here, this is the floor function, this is the ceiling function. Okay, so that's for both sub-arrays. This is for left sub-array. This is for right sub-array. Left sub-array and right sub-array. And this is for, that is for the merging step. Number of comparisons for merging. All right. So this is the corresponding formula, which is an implicit formula. All right. In the next slide, we're going to talk about tractable and intractable problems. This is a quick subsection that we are going to cover in 3 slides. At an opposite extreme for an algorithm such as binary search, which has logarithmic order, is an is an algorithm with exponential order. All right, so you know the binary search, which has logarithmic order, but there are some algorithms with exponential orders. All right, so there are algorithms with exponential orders. That means very expensive. Okay, they are very expensive. For an example, consider an algorithm to direct the movements of each of the 64 disks in the tower of Hanoi Puzzle. I don't know whether you are familiar with this puzzle. This is called Hanoi Puzzle. I will explain that in a second. As they are transferred to one by one from one pole to another, we know that such a transfer requires 2 to the power 64 minus 1 steps. So it requires this many steps. This is the Hanoi puzzle with 64 disks. Let's assume Hanoi puzzle with 3 disks. Okay, so I'm going to explain this Hanoi puzzle with 3 disks. Okay, so this game is like this. It has 3 poles. So then one pole has 3 disks like this. So you have to move all these disks into another pole. They look like in the same order, so they should lie on the same order. That means the smallest at the top, the largest at the bottom, and the medium sized one in the middle. Okay, so you are allowed to move one disk at a time. Okay, you are allowed to move one disk at a time. So let's see how many moves that you need. So next thing you would think is you could just move that one here. So it will look like this. And then this goes there. And then in the next move, what happen is the single one is here, that one is here. You move this one over there, and then that one goes there. And in the next step, what we do, we move this one over here. Okay, in the next case, you move this one over there. And then finally you move this one over here. Actually, I made a mistake. So you are not allowed to keep like this. You are not allowed to keep like that. So this is not the triangular shape, all right? So you are not allowed to keep like that. So let me redo this problem. So I made a mistake over there. So I'm going to delete everything. You always have to keep them as a triangle. All right. So the next thing what you could do is in the next step what we do is let me delete that. We take this to that pole. So it will look like this. The bigger one here, small one here, medium one over there. And in the next step, we bring that one over there. So this is the biggest one, medium one, the small one. In the next step, we bring that one over here. So this is the biggest one, and then this is the medium one, a small one. And in the next step, we bring that one over here. So then it will look like the biggest one, medium one, and small one. And then we bring this one over here. In the next step, it will look like the biggest one, medium one, and the small one here. And the final step, we bring that one over there. Okay, the puzzle will look like this. The biggest one, the next biggest one, small one. All right, so that's how you move from one pole to another pole. So let me count how many moves. Move number 1, 2, 3, 4, 5, 6, 7, right? So there are 7 moves. So there were 3 discs. Okay, there were 3 discs. That means number of moves equals 2 to the power 3 minus 1, which is 8 minus 1 is 7. Alright, so that's how you get number of moves. For n disk, number of moves equals 2 to the power n minus 1. Alright, so that's what given here. Let me rearrange this. Let me take this one over here. Alright, now let me read this. Now you understand how this number comes. 2 to the power 64 minus 1 steps are there for a Hanoi puzzle of 64 discs. If a computer took a nanosecond to calculate each transfer step, the total time to calculate all the steps would be this many. So this is the number of steps, so, number of moves, and then this is the time that the computer takes to make one move, 1 nanosecond, and then you have to multiply that by 1 over 60 to make it into minutes, and multiply by 1 over 60 again, make it to hours, and 1 over 25 to make it to days, and then 1 over 365 times 225 to make it number of years. To solve this puzzle, the computer takes this many years. All right, the computer takes more than 500 years to solve this puzzle if the computer takes a nanosecond to calculate each transfer step. All right, you can see how much time it takes. So this is actually a exponential order problem. This is actually an exponential order problem. All right, so you can see it takes a lot of time. Okay, so this is an exponential order problem. Let's move to the next slide. Now we are going to learn about a few technical terms. Problems whose solutions can be found with algorithms of worst case order with respect to time is a polynomial are said to be class P. They are called polynomial time algorithms and are said to be tractable. If it is polynomial times, we call it they are tractable. Problems that cannot be solved in polynomial times are called intractable. All right, so this section is about tractable and intractable. So these are the definitions. Okay, if they are solved by polynomial times, then they are called tractable, and otherwise they are called intractable. These are just technical terms I'm just presenting here for your knowledge. Okay, so these are not much meaningful your homework questions or exams. For certain problems, it is possible to check the correctness of a proposed solution with polynomial time algorithms, but it may not be possible to find a solution in polynomial time. Such problems are said to be said to belong to class NP. Okay, so the previous it was class P. This P stands for polynomial. This is NP. This NP stands for non-polynomial. Okay, so this NP stands for non-polynomial. Okay, let's go forward. The biggest open question in the theoretical computer science is whether every problem in class NP belongs to class P. That's a problem. Nobody knows still. Okay, that's a problem. It's an open problem. Nobody knows. Open question, which is every problem in class NP belongs to class P. This is known as P versus NP problem. All right, so a little bit of information here. The Clay Institute in Cambridge, Massachusetts has offered a prize of 1 million to anyone who can either prove or disprove P equals NP. So this is something not yet done. So if you are smart enough, you will be able to get this prize, which is $1 million. In recent years, computer scientists have identified a fairly large set of problems called NP-complete that all belong to class NP but are widely believed not belong to class P. Okay, such problems are called NP-complete problems. One NP-complete problem, commonly known as the traveling salesman problem. All right, you might have learned this problem early in optimization class. Normally, this problem is introduced in linear algebra class. If you have taken a linear algebra, maybe optimization class. You might have learned this in a linear algebra class. I'm sorry, not linear. What I want to say is linear programming class. In a linear programming class. All right. So if you haven't learned that, that's all right. You don't need to know that. So this is the end of the section. From next day, I'm going to start the new chapter, chapter 12. Thank you very much.